I'm Monet. I will be presenting Lab 2, Motion of a Falling Object. So first I'm going to get into the contents of this lab, what we'll be exploring. We'll be looking at a lab introduction before getting into the observations, code modifications, before we get into a data analysis and comparisons, and finally our conclusion. So the introduction for this lab consists of its purpose and the fundamental concepts, those being drag force and gravitational force, or weight as we call it. And the purpose of this lab is to observe gravity and drag forces effects on a falling object. To do so, we will track the motion of a paper ball falling. So to get more into these fundamental concepts, we have gravity, which is demonstrated here, drag force demonstrated here, and Newton's second law shown here. Gravity is the force that attracts a body towards another physical body having mass, and drag force opposes forward motion in the atmosphere. B is the dampening coefficient, and it's a property of the material. And this force, drag force as a whole, is dependent on the velocity of the object. Acceleration. For Newton's second law, acceleration is directly proportional to force, and force is defined as the rate of change of linear momentum. Furthermore, these are other concepts or equations that are going to be important to this lab. This is the position update formula, and this is a velocity defined as the change in position over the change in time. So as we get into our observations, first, we have to define the system and the surroundings. And the system would be the paper ball. The surroundings would be gravity and my bedpost, which the height was measured from. And here, listed here is the initial condition. So here are the graphs that I collected from Tracker and GlowScript respectively. The data collected from Tracker shows this kind of parabolic curve, and the same is true for the GlowScript model. This being the model that accounts only for gravity, and the Tracker model being collected from a video. Into the GlowScript model, and again, this is the one that accounts only for gravity. These are the according changes I've made. First, starting with the ball mass, which I changed to match the weight of our paper ball. And next, I made the ball position and the ball velocity vector, the 0 vector, to match my initial condition. Down here, I've changed Fnet to be to account only for gravity in the y direction, because this is the only force acting on the ball per this model. And of course, this is based on F equals mg, the formula for weight. Lastly, on this slide, I changed ball velocity here to model the position update formula by making it Fnet over mass times delta t. So this here is our model accounting only for gravity. This model here accounts for drag force as well. And to look deeper into that, what I changed about this model was first changing B, the dampening force, because when it is 0, it represents no drag force. So of course, this had to be updated to include drag force in our computation. And here, Fnet is changed to account for the drag force in addition to gravity by adding ball mass times G times J hat to this equation here, which models drag and gravity. Here is our final graph plotting all three of these, the observed data, the model with drag and the model without drag against each other. And as you can see, the observed data is closer to the model with drag than it is the model with no drag. In conclusion, what does this mean, and which model predicts a better terminal velocity? Of course, the model without drag force shows a constant velocity, which is inaccurate to the real situation. So the model with drag predicts a terminal velocity better. If the velocity were to be initially thrown downward, how would this change terminal velocity? Well, terminal velocity would remain the same in this case because terminal velocity is dependent on the forces acting on the object, which would be the same in both cases, gravity and drag. Thank you. That is all.